Our next speaker is Yuqi Jiao, who is a first-year PhD student at Politecnico di Torino, supervised by Professor Marco Melia. And his research interest lies at the intersection of network traffic analysis and artificial intelligence.
So, okay, good afternoon. I'm Yuqi, a first-year PhD student from Politecnico di Torino. Today, I want to show you our recent work, The Sweet Danger of Sugar, Debunking Representation Learning for Encrypted Traffic Classification. So quickly remember, what is network traffic classification? So it is to identify and categorize network traffic data. For example, identifying which website a packet or a flow belongs to. Well, with the development of AI, more and more researchers are using AI in these problems. And they try to use a supervised learning way to find the potential patterns from the training data and training models. But there are some literatures. They declare that there are some limitations of supervised models. For example, label quality data bias. So take a label quality as an example. If the model training with low quality data, so it cannot fit various environments and various traffic data. And thus, so people proposed a new way, the representation learning. So it doesn't rely on supervised learning. It is based on self-supervised learning, which means you don't need to have the labeled data. And we can see a quick example. So image recognition. And we can say this is a basic architecture, the encoder-decoder. So here, the researchers would like to try to segment the picture at first and masking some part of the picture, and then try to reconstruct it. And during this pre-training stage, the model, especially the encoder part, they could learn the potential patterns and the potential relationships, which we call the mask and the mask autoencoder. Then, once we have the encoder architecture here, we can use it for the real-world scenario, that is the downstream tests. So we use the same encoder, which means the same architecture and the same parameters. So here we still see it's a classification test. So it's a classification what image it is. So that is cat. So what if the scenario in the network domain is similarly? So now we have the pickup files, which contains network data, network information, and then we try to segment it, mask, and reconstruct it. And then we get the powerful encoder, so we could get the powerful embedding. And for the downstream text, similarly, we use the same encoder for the classification. And for example, here we try to check the traffic if it is a VPN or no VPN. So what's the problem? So the problem we focus on is a network traffic classification task. Specifically, we'd like to do the 120 classes classification, which is classifying each single packet into 120 websites. So everything is encrypted. Let's look at the image, the figure. So each line represents a flow, while different color represents different websites. And here, we'd like to take one packet from the flow and check its labels. So how the performance of current work, how the performance of the outstanding works. We investigate some works from the top conference, KDD, III, and so on. And we can see they could get very good performance. Most of them get 80 and more accuracy here. And some of them declare that they could find potential patterns from large-scale unlabeled encrypted traffic data. So here, we have a question. Do we agree with this, that they found potential patterns from encrypted information? Or should we trust those ones? So do you know those three? Those three are the inventors of RSA, the very famous encrypted algorithm. So here we believe those three more. So with the research question, what are pitfalls in representative learning for our domain? And if there are, what are they? So let's consider how to design the representational learning. So here we list several, outstanding models here, and try to show you the totally design win. It's very quickly, and we mainly focus on the three parts. So let's see. So at the beginning, we try to design a model name, and then we try to design an architecture. Then, if we have architecture, try to design the pre-trained tests. And if we have tests, we need to decide which data set we use here for pre-training. Then we got the pre-trained model, then downstream. So if we have the real-world scenario, so how to clean the data set, how to split it into train and validation and test set, and then finally, what's our training strategy? So here we mainly focus on the three types, and for the other, if you are interested, please check our papers. So firstly, the task type. In order to learn the generative patterns from the pre-trained tests, the researchers would like to follow previous architecture works. So the common way is the masked autoencoder, which we showed previously. So it's like masking and reconstructing the packet bytes. But there is a problem. Some research would like to consider the encrypted payloads for the MAE. But we all know the encrypted payloads lack the correlations. So probably it's not so effective for that model for reconstruction to get the powerful encoder. So here we suggest that try to avoid the pre-trained tests on encrypted payloads instead of focusing on unencrypted information. Next, split. Ideally, we'd like to get a testing data set with independently and identically data distribution and with respect to training set. So here, people would like to do the per packet split solution. So what it is. And we can also check the right figure. So as we know, the green part is a flow, and the blue part is also a flow. So here, for per packet split, people would like to take some packets in the training set, and they would also left the other packet in the test set. And they try to remove the implicit flow ID, as we know, that is IP address and the port information to exclude the implicit flow ID. But they omit another thing, the implicit shortcuts, which I will show you later. And the other split way is per flow split, which means packets from the same flow only appear once. Also, for red figure, we can see for the yellow flow, it appears twice in training and test set during the per packet split, while for per flow split, it only appear in training set. So we suggest that we should always adopt a per flow split. So how the performance changes between the per packet split and the per flow split. This is the previous results, the original results we already seen. And when we add the per flow settings, we can see the performance drops a lot. So this is mainly due to the implicit flow ID. So how implicit identifies our sweet sugar? Let's look at an example. Sequence number. As we know, the sequence number is continuous within a flow, but it's different across different flows. So here are two flows, and as we know, and they have different sequence number. So the packet, the sequence number of packet close to the X0, so it could be, the model can easily to learn it should be the green part. While the packet, the sequence number of packet close to Y0, the model can easily to learn. This is the blue part. So the X0 and the Y0 are implicit flow IDs, and the model can easily overfit to flow IDs instead of learning the traffic patterns. And there are some other implicit IDs we discussed in our paper. If you are interested, please check. And the last one, the training strategy. So the reason why we use the representative learning is that we want to learn generative embeddings, which means we want to use this embedding for many downstream tests. So we want to use the knowledge from the pre-train more and more. Well, here people would like to use an unfrozen encoder phase. So which means when we have the network traffic data and we input it to the encoder and get the embedding, and finally we use the embedding for classification. So here the problem is the unfrozen, when we train the model, the research would like to train the end-to-end model, which means the parameters of classification head will be updated, and the encoders, the parameters of encoders will be also updated. So this end-to-end. The other option is only train the classification head. So we only update the information of the head. So for the frozen encoder, we could get less computation, and also we could use pre-trained knowledge, the pre-trained knowledge from the large unlabeled data. So we could use the useful knowledge instead of covering it again. So we suggest that always adopt a frozen encoder. Also, let's check how the performance change. So this is the correct way, the per flow split, we already know. And when we add the frozen setting, still everything drops. So which means those encoders do not learn any actionable representation. So in order to mitigate those pitfalls, we proposed our model, pickup encoder. So it is based on T5 architecture, that is question and answering architecture. So for pre-trained data set, we use a different and larger data set, and we try to focus on the header information, so we omit the payload information. And also for pre-trained tests, we mainly do the text on the header, so try to mask and reconstruct it, and try to ask a question to the models. And finally, for downstream classifier, we use the frozen and the per flow split way. So what's the performance of our models? It's good, especially on the per flow split and the frozen encoder settings, which means our model learns the protocol semantics and the format, and it could extract the proper features. So here we know we want the model to extract the features. So what if we directly use a feature to the shallow models? So here we extract the field information manually and put it to the shallow models. For example, the random forest. We can see the performance is also very good. It's similar with pickup encoder, and it exceeds other models. Why? So in our case, we think for shallow model, this is because the shallow model, it uses domain knowledge directly. It uses field information directly. Well, for pre-trained model, you need to learn the information from the raw bytes via the pre-trained test. So the next is, what about the model efficiency? So we try to calculate the training time and inference time here. So we can say, obviously, the shallow model is the fastest, while the other model is slower than it, varying to some degrees. So now we consider another question. So is the representation learning still works because you need to make a much effort and to get similar results with shallow models. In our case, it's an open question, but our answer is yes, because it could automatically do the feature engineering. That is, you try to learn something from the unlabeled data, from the traffic, and then the model could extract the information. So we don't need the domain knowledge. We don't need the expert knowledge here. So what's the lesson we've learned? So firstly, beware of that the deep learning models are easily to leverage the shortcuts. So here we need to verify the data integrate. That is, try to free from the data linkage artifacts or even the spurious correlations. And then when we get the representation learning model, we should assess their carefully. For example, try to use the frozen way to evaluate the encoder carefully. And finally, when we design a model, we should consider the time cost. And that's all. Thanks for your attention.
Thanks for the talk. Questions for Yuqi? Yes.
Hi, so what's the approximate size of your model?
Model size?
How big is your model?
For pickup encoder, it's the size of the pre-trained model is about 800 megabytes.
Thank you very much. One question, you mentioned the comparison between random forest and your model, right? Does that mean the random forest using label data, supervised learning, while your model, you don't need the label data and it can learn by itself?
So do you mean, so here for random forest, we use the supervised learning model directly. So there is no unlabeled data. So here we only compare the performance for the downstream test. So we use the labeled data.
Sure. Another question is, can you explain a little bit more about the Q&A style model that you used?
Yes, because it is, so we use T5-based architecture. So at the beginning, it is like so it's like with the question and the task. So like, so here it's like, what's the place of the SIGCOMM'25, and there is the answer. And finally, the model will answer the question. So it's similarly in a network domain. So it's like the question, like what is the TTL, and the network packet, and then answer the question.